We perform an experiment in our laboratory operation using the PET simulator provided for us. After the trial are complete and the result of each trial are listed, we then continue to observe and evaluate the result. We used to have a constant distance between the charge to the complete understand exactly what is happening and also have a multiple trial using the constant same charge to be able to observe. The variable has the greatest influence on the resulting phi. It is stated the Coulomb law that the force between the 2 points will be proportional to the magnitude of the charge of the 2 points. And if you take into account the distance of the charge, the reverse will be true. In short, the law of the Coulomb let us define where the electrical field path leans toward.
Procedure. First, we use the PET simulator given on the canvas. We open the macro scale, then we scale the charges for 5 trials. On the first collection of data, the distance of the charges was kept constantly. The first force was placed at 0 centimeter, the other at 7 centimeter. The constant distance that we were using was 7 centimeter. We used 8 microcoulomb and 8 microcoulomb for the charges and 7 centimeter for our constant for the first test, resulting in a force of 117.388 Newton. We raised the value of the charges for the second trial and used 5 microcoulomb and negative 2 microcoulomb, resulting in 18.342 Newton. We continued to raise the value of charges for the third trial, using 3 microcoulomb and negative 1 microcoulomb, resulting in 5.503 Newton. We used negative 8 microcoulomb and 6 microcoulomb for the fourth experiment, resulting in 88.41 Newton. We then used 4 microcoulomb and 5 microcoulomb for the fifth and the last scale for table A, resulting in 36.684 Newton. The quantity of charges was negative 9 and 7 and was kept constant for table B, and we also scaled it for 5 trials. The distances between charges is 8 centimeter and it resulted in 88.471 Newton for the first trial. For the second, the distance between charges was 4 centimeter, resulting in 353.885 Newton. The distance used for the third trial was 2 centimeter and the result was 1,415.539 Newton. The distance for the fourth experiment was 5 centimeter and resulted in 226.486 Newton. And the final distance for table B used was 6 centimeter, resulting in 157.282 Newton.
Hello, my name is Christian Gerentillo and this is Laboratory Experiment 1 for Coulomb's Law. Now, I'm the one who made the values for our table and I will be using PET simulator to get those values. Now, for table A, the distances will remain constant from numbers 1 to 5, while our nanocoulomb or charges of Q1 and Q2 will differentiate from numbers 1 to 5. And our value of F will depend on the values of Q1 and Q2. So for our distances, we'll make it very simple and we'll have a distance of 7 centimeters or 7 meters. And for our nanocoulombs or charges, our Q1's charge will be at a positive 8, while our Q2's charge will remain the same. So we'll have a value of 117.388 N. Now for number 2, for our Q1's charge, we'll make it positive 5, while our Q2's charge will make it into a negative 2 value, so we will have 18.342 N. Now for number 3, our Q1's charge will be positive 3, while our Q2's charge will become negative 1, so we'll have 5.503 N. Now for number 4, we will make Q1's charge into a negative value, so we will make it into -8, while our Q2's charge will make it into a positive, so we will make it into a value of 6, so we will have 88.041 N. Now for our number 5, we will make charge 1 into a positive value again, and we'll make it into a charge of 4, while our Q2's charge will make it into a value of 5. So we will have a value of 36.684 N. For table B, the process is still the same using PhET simulator, but instead of the distance being constant from numbers 1 through 5, what is now constant is the amount of charges in nanocoulombs or the charges of Q1 and Q2, and the forces between the charges will now depend on the value of the distance. Now, if we go back to PhET simulator, the charge of Q1 and Q2 will have a constant charge. So for charge 1, we're gonna have a charge of -9 and charge 2 at a +7. So for the distance, we're gonna place Q1 at 9 centimeters, while Q1 at 1 centimeters, bring us the value of 88.471 N. Now for the next distance, we're gonna place Q1 at 3 centimeters and Q2 at 7 centimeters, bringing us the value of 353.885 N. For the next distance, we're gonna place Q1 at 5 centimeters, bringing us at 1,415.539 N. For the next one, we're gonna place Q2 at 10 centimeters and bringing up to a value of 226.486 N. And for the last one, we're gonna push back Q1 to 4 centimeters and bring us a value of 157.228 N.
We have observed that the experiment successfully accomplishes the given objective, which was to verify the principle that governs the Coulomb's law for electrostatics, which state that the electrical force between two charged objects is directly proportional to the quantity of charge on the objects, and inversely proportional to the square of separation distance between the two objects. In Table A, the distance between the charges is held constant. As seen in the results of our attempt at experiment, the force between the charges increased with the quantity of charges. Therefore, verifying that the electrical force between two charged objects is directly proportional to the quantity of charge on the objects. This time, in Table B, the amount of charges are held constant rather than the distance. The results of our trials confirm that the electrical force between two charged objects is inversely proportional to the square of separation distance between the two objects, as it is shown that the amount of force decreases the higher the distance is between the two charges. Therefore, the two values are inversely proportional, verifying Coulomb's law for electrostatics.